Okay, next exercise. If x is inductive, then this set of all x and x such that x is transitive and not an element of itself is also inductive. From this we infer various things about big N and its elements. Again, I call x prime this thing I'm trying to show is inductive. Again, I skip the easy parts and go to the hard part, which in this case is showing that x prime is inductive, so any a and x prime, then I want to show that a plus 1 is transitive and not an element of itself, so that a plus 1 gets into x prime. So, in fact, showing that a plus 1 is transitive goes exactly as the previous exercise did, since that's essentially the same thing. You just get extra assumptions, but that doesn't get in the way of showing that a plus 1 is transitive, so I leave that to go do some archaeology in the previous exercise and find out how that went, if you're not sure. But for the part where we argue that a plus 1 not an element of a plus 1, that's the hard part. Let's suppose for contradiction that a plus 1 is an element of a plus 1. Well, that must mean that a plus 1 is either an element of a or equal to a. We've seen that principle repeatedly now. In the former case, since a itself is transitive, and a plus 1 an element, therefore a plus 1 a subset. Well, in that case, everything in here must be in here, so in particular, if I take a, I can infer that a must be an element of a, but we knew that we selected a from x prime, which therefore is in this set, and therefore none of these such things are contained within themselves, so there we derive a contradiction. A is in A, and yet because of this A is not in A, and so we have our contradiction. In the remaining case, if a plus 1 is equal to a, and again recall that a plus 1 is equal to this union, well, exactly the same argument applies, right? We have something even stronger than a subset, but still we have access to the fact that everything in here must be in here, and again you get a, an element of a, which is again a contradiction. Okay, for the upshot, we would like to show that no natural number, or no element of this set n, is an element of itself, nor is it equal to its successor, so to speak. So, yet again, we observe that this set can, the principle that we just proved about all inductive sets applies to n, and therefore n being the smallest inductive set is a subset of that. Pick any element out of n and it has this property, so that immediately tells us that no elements of n are contained within themselves element-wise. To show that no element is equal to its successor, just notice that the successor contains an element which the predecessor does not, namely m itself. So there you have it.